This episode of the HVAC School podcast is made possible because of the generous and ongoing support from our sponsors, Testo, Carrier, and RectorSeal. And I wanted to talk a little bit, just real quickly, about the Testo 115i. Testo 115i. It is a wireless temperature clamp that has recently been proven to be even more accurate generally. And Testo doesn't say this, and they're not telling me to say this, but recently Jim Bergman did some testing with the Testo 115s and some of the 605i's and other things with his Measure Quick app. And so Jim, as you know, Jim's been on this podcast a lot. He actually went to NIST, N-I-S-T, which is the National Institute of Standards and Testing or something like that. I don't actually know exactly what that stands for. I should have looked that up beforehand, but you get the point. They are the governing body that helps sets the standards for these sorts of things. And it was proven when compared to extremely expensive pieces of test equipment that the Testo sensors that they're using in their smart probes devices, which with the 115s being an example of that, are extremely, extremely accurate. And like I mentioned, you can use those with the free Testo Smart Probes app, or you can use them with the free Measure Quick app that Jim Bergman put out, and you can actually do some pretty cool things with those probes. But I want to talk specifically about the Testo 115s because today we're going to be talking a little bit about heat pumps, actually quite a bit about heat pumps. And one thing that you'll notice when you're checking a heat pump is there's some things that are tricky to check, specifically suction line temperature on most heat pumps, unless you have a wireless temperature probe. Running that wire in there to get a connection on the suction line can be really tricky, which is where the Testo 115i's come in really handy. They're very reasonably priced. You can find them at TrueTechTools.com. As always, our offer code is GetSchooled for a great discount. But that is the Testo 115s. I use them all the time. They have actual thermistor sensors as opposed to thermocouples. If you're used to those little brown wires, or even some of the clamps, temperature clamps that are out there, most of them are thermocouples, not thermistors, and so they're not going to be as accurate in most cases as the Testo 115s. So check them out. Testo 115i's. You can find them where any high quality products are sold, or just go to TrueTechTools.com.
This is the guy who gets excited whenever he learns something new about HVAC, which is every day. Which means he is always a little too excited. For a grown man. Brian Orr.
I'm going to try to stay calm here. Those of you who know me well know that I am not actually an adult man. I am just a child pent up in a chubby adult man's body. Once again, we have Carter Stanfield on the podcast. Carter is one of my favorite educators out there and a really nice guy. And we were having a conversation, which I'm going to kind of recap in the podcast. I'm not going to give away all the details yet, but we were having a conversation and he pointed out the importance of compression ratio. And I've been wanting to have a compression ratio podcast for some time, and so the day has finally come. But this is not just a compression ratio podcast. No. This is actually a pretty good look at heat pumps and why they are the way they are, and some of the challenges with heat pumps, specifically as it relates to setting a charge, why the pressures are what they are, and some of the other things about heat pumps. So I think this sort of has a dual purpose here. You can learn a lot about compression ratio and learn some things about heat pumps. Frankly, something about heat pumps that I really never understood about the infamous charge compensator on Roods and Reams, and so Carter reveals the details of that for us. So here we go, Carter Stanfield talking compression ratio and heat pumps. Today on the podcast, we have Carter Stanfield. This is Carter's second time coming on the podcast, so he's an old pro, so thanks for coming on again, Carter.
I'm glad to do it.
So I'll just kind of set the stage of how we decided to do this episode, because I wrote an article about, it is actually a republish of an article that I wrote way back before I even had any business writing articles, but I wrote it for my former employer before I started my own business about checking the charge, checking the system on heat pumps, because it was always a challenge in heating season. Once the outdoor temperature dropped below 65, what is the best way to check the charge on a heat pump? So I wrote an article on it, just some of the tips, things that some old timers taught me and some things that I've practiced over the years, because we work on a lot of heat pumps here in Florida. And after I published it, Carter commented on one of the Facebook posts about it that part of the challenge here has to do with compression ratio. And compression ratio is something I understand, generally speaking, but I know you understand it a lot better than me. So let's start at the beginning when it comes to compression ratio. What is it, and why should it matter to the average technician?
Well, to start with, a ratio is really just a comparison of two numbers. So with compression ratio, we're comparing your discharge pressure to your suction pressure. And when I say compare, we mean divide. So you're dividing your absolute discharge pressure by your absolute suction pressure. In essence, you're really just seeing how much you're squeezing the gas. So if you have a compression ratio of, say, 3-to-1, that means that your discharge pressure, your absolute discharge pressure, will be 3 times higher than your suction pressure. Why it's important, if you think about it, if you're asking your compressor to do two things, we're asking it to move gas, and we're also asking it to make this pressure. If you ask it to do more of one thing, then naturally it does a little bit less of the other. So if we ask it to make more pressure difference, then we don't move as much gas. And when you think about moving the gas, it may not be immediately obvious how much gas we're moving, but to just give some quick and dirty numbers, 410A, you're absorbing about 120 BTUs for every pound that evaporates. So for a ton, you need to circulate 100 pounds of that stuff an hour. You're doing a fair amount of work in terms of gas circulation. If you ask the compressor to make more pressure difference between the low side and the high side, then you can't move as much gas. Basically, you have sort of a fixed amount of work that you can do.
One way that helped me think about this, because only recently have I started to really get my head wrapped around it, because there's two sides of the equation, obviously. There's the head pressure, and then there's also the suction pressure. But if you think about it in terms of on the suction side is where the compressor is getting its refrigerant from. And so the compressor has a fixed volume in the head of that compressor. If you think of a piston compressing, there's a fixed tolerance in between the top of that piston and the cylinder head. And so that gap is a fixed volume. But the actual mass, the actual number of atoms changes depending on the density of that gas. And we know the density, we can see that by looking at the pressure of it. And so when you have something that has lower pressure, that volume remains the same, but that gas is lighter coming into it. When you have lighter gas, you are naturally going to tend to move less of it. There's less of it entering the head of that compressor. So is that a good way of thinking about that? Or is there a way that you would maybe amend that to make it more easier to understand?
That's correct. An analogy that I like to use, like all analogies, it's not exactly right, but it gets you in the ballpark. A lot of people understand about water pumps and the head on water pumps versus gallons per minute moved, and how if you ask the pump to move the water up 10 feet instead of 5 feet or 20 feet instead of 5 feet, that you get less water moved. And all, pump curves and things will tell you that. And the little pumps like we work with, like the condensate pumps, usually have like a point at which they don't move anything. But anyway, most people understand that in water pumps. And basically, it's kind of the same. The compressor is just a vapor pump. The main difference is that unlike water, the gas can squeeze some. So that changes the dynamics just a little bit.
And so if you think about it in terms of compression ratio is taking into account the head that you're working against, the amount of pressure that the compressor has to work against, as well as the actual mass of the refrigerant coming in. And so it's taking that differential, and the greater the differential, the more that compressor has to increase the pressure of that refrigerant, the less refrigerant is going to move, which is essentially what you said earlier, but you can think about it on both sides of the equation. So if you have a system that's working perfectly good on a 75 degree indoor temperature and a 90 degree outdoor day, and it's just humming along beautifully, and you walk up to it and block the condenser off to it, and you drive that head pressure up, you're going to move less refrigerant because you're forcing that compressor to work against a higher head pressure. And in the same way, if on that same unit you go inside and you reduce the indoor load by blocking off the return air grill, well, then you're going to reduce the amount of heat that's entering the refrigerant, and you're also going to reduce the density of the refrigerant that's entering. You're dropping the suction pressure, and that would also increase your compression ratio, which would reduce the amount of refrigerant that you're moving. And so you can think about it either way, but the compression ratio just takes into account both sides of the equation.
And something mentioning the effects of both the high side and the low side, something a lot of people don't realize is that the low side, changes in your low side pressure actually affect your compression ratio a lot more quickly than changes in your high side pressure. So, for example, if your low side goes from 40 to 20, that's a much larger percentage change than if you go, say, from 250 to 270. So if you work through just a little bit of math, you can see that stopped up filters and blocked coils and things have a big effect on the compression ratio. Not that plugged condensers don't, but evaporator will mess up your compression ratio a lot faster than a condenser will.
Yep. And two things that I want to mention quickly before we move on and get anybody confused. You made a really important distinction that it's the difference between discharge and suction. So it's the refrigerant right before it goes into that compressor and the refrigerant right after it goes out of the compressor. So you can't compare suction pressure to, say, liquid pressure and get a true compression ratio. Is that correct?
That depends a lot on the system and how much pressure difference there is between your discharge and your liquid. But because you've got a lot of piping and sometimes some components besides the condenser in between your discharge and your liquid, you could get some funny things there. With like a typical residential air conditioning system, there probably is not a lot of difference between your discharge and your liquid. But you get to, say, a commercial refrigeration rack system, and there could be a big difference.
So you had also mentioned the absolute pressure. So when you say absolute pressure, how is that different than gauge pressure?
With your standard gauges, if you have them open to the air, the gauge reads 0. Every pressure reading we take with those gauges, we're reading how much pressure we have above atmospheric pressure. But the truth is, at atmosphere, we really don't have 0. We have almost 15, somewhere around 14.7. So absolute pressure takes that into account. So if you were to use a set of gauges calibrated to absolute pressure, when you unscrewed your hose before you even connected it to anything, you'd be reading about 15 pounds. And then when you read your refrigerant pressure, it would be about 15 pounds higher than what we typically see in our gauges today. So the conversion is pretty simple. You just add your atmospheric pressure to each of your suction and discharge pressures. For most purposes, 15 works pretty well. But if you want to be really accurate, you can actually measure your barometric pressure, look it up for that day, and add to it.
Because it can vary both, like you mentioned, barometric pressure. It varies day to day even in certain places. But then say you're way up in the mountains, then it would be slightly lower as well. So again, this is really getting really fine and detailed here. But that's why they have that, because when you're looking at it from an engineering standpoint, you do want it to be very accurate and detailed. The point is, when you're calculating compression ratio, you don't just take the pressures that you read and divide the suction into the head pressure. You have to first add approximately 14.7 to each. That's a sea level number in order to get that exact number before you do your division.
And it can make a pretty big difference in terms of your actual answer.
If you forget to do it whatsoever.
Right.
For sure. Okay, so now let's move into some of the circumstances in which it matters. And so let's focus first on what we were originally discussing, which is in heat pumps and why the dynamic changes in compression ratio can really affect the operation of the system.
One of the things that makes working with heat pumps, in particular heat pump charging in the heating season, a challenge is that the amount of refrigerant moved varies quite a bit depending on the conditions. So the amount of refrigerant moved, I'll pull up this little chart I'm looking at. I'm looking at a Goodman performance chart of a unit that has an HSPF of 9. So this is not a super high efficiency unit. It's just sort of a middle of the road sort of unit. And it's a 1.5 ton unit. So at 47 degrees outside, its capacity is 18,000 BTUs, which is pretty much exactly the same as the cooling capacity at 95. At 10 degrees, however, its capacity is only 9,400 BTUs. So pretty much half of what it is at 47. And the reason is because at 10, my evaporator pressure and temperature are going to be much lower, so that the compression ratio is higher. The compressor just can't move as much gas. So you're moving about half as much refrigerant when it's 10 degrees outside as you are when it's 47 outside. For charging purposes, where that presents a problem is if I'm trying to charge it in heating and it's 10 degrees outside. Once I get, say if I was going from absolutely nothing, once I get half the charge in there, my pressures are actually going to be correct because I'm moving all the refrigerant that it can move at that point. And I still, though, I've only got half the charge in. The other half the charge is basically sitting somewhere when the unit's charged up right, but it's hard to tell if I've got that other half a charge sitting in my accumulator or in the coils somewhere. And that's why a lot of manufacturers don't particularly like you trying to add charge to it on the heating cycle.
Very interesting. Yeah, and I remember, even to this day, I don't completely understand how this component works, but I remember back in the day, we used to have a lot of trouble, for whatever reason, with ream heat pumps in heat mode. They would have a lot of issue where, they would go out on high head. And I think a lot of it had to do with the way the ductwork was installed in the air handler. So they were running low airflow in a lot of cases. But they used to have a little component called a charge compensator that they would install in there. And that was the general idea, is it kind of gave a place for that. It was almost like a little mini receiver where it gave a place for that additional refrigerant to hang out whenever it was in the heating mode. Have you ever seen something like that?
Yeah, and I can explain both what it does and why Ream in particular had a problem with that.
Oh, great. Please do. This is something I actually do not know the answer to, and it's been probably 8 years since I've seen one.
Those indoor coils that they had, may still have, but look like an M or a W, small diameter single row pipe going up and down. They don't have very much volume in them. And they're heat pump blower coils. If you look at heat pump blower coils that they made, they had flanges for your ductwork, but they weren't on the outside of the blower. They were kind of in the middle. And it had a big orange sticker on them, and it said, "Fold this up." A lot of people didn't do that. It literally saved them an inch in shipping, basically, is what it did. But if you didn't fold it up, it was blocking the airflow. It also told you in the instructions that the ductwork was to connect to those flanges, which were kind of in the middle of the unit, not on the outside. But everybody, doing what they always do, put their plenums on the outside. And that blower, they save space by cutting off the straight part of the blower. And when you look at a centrifugal blower, it kind of slings the air in all directions, and then the straight part coming off the blower straightens it out and gives it direction. If you don't have that straight part, then the blower doesn't perform as well. So if you don't hook the ductwork to those flanges that they gave you, there's no straight part to the blower, and the blower doesn't move as much air. So then what happens when you go to check the charge in the cooling season and you're not moving as much air? Well, people would fix that air problem by overcharging it to try to bring the suction pressures up and keep it from freezing up. Well, now they have too much refrigerant in it. When it got to heating, those coils couldn't hold all that extra refrigerant, so it would be popping the pressure switch all the time. So I knew people that would every summer, or every spring really, go out and add charge, and then every fall go out and take it back out. And it was because of an installation error.
It's funny because I have a house in mind. I was probably 19 years old, and I had to go back to it a couple times, and I can picture the house, I can picture the unit, and I was running into this exact problem that you're identifying. And sure enough, I mean, at the time, you're thinking, well, if you attach the duct on the outside of the unit, that's better because you're giving it more airflow, right? I mean, that's the thinking that my young brain had. But now that you're bringing this up, it's just bringing back all these memories. But very interesting stuff.
There is a way to put this plenum on the outside if you just absolutely have to do that. And you put like a 1-foot collar on those flanges. So what you do when you do that is you effectively put the rest of the blower on there, the part that straightens it out. Then when you put your plenum on the outside, you have to make sure that it's long enough that any takeoffs are a good ways away from the end of that collar that you got inside there. It all came about because they did some unusual things with their heat pump blowers, and they were clever, but they were different. And people a lot of times in industry aren't really too good with different, especially if it requires reading and following a set of instructions. So that's why they had airflow issues. Now, you can run into that same problem with anybody's heat pump, not just those old Rheem ones, but because they did some things that were kind of different, they gave some people some headaches. The charge compensator, what happens with that is a little bit like a liquid receiver. If I can put a plug, it's actually in the book in the heat pump section. The only thing is it's different. In a liquid receiver, you have an in and an out for your liquid. In a charge compensator, the in and the out is just one pipe. You have one pipe that's hooked to that cylinder that goes to the liquid line. And then the gas line that goes to the outdoor coil runs through the charge compensator. So it's not opened up to it, it just literally runs through it. Now what happens is when you're in the heating cycle, that gas line is cold because it's basically the suction line, creates a low pressure in that tank, and it sucks any liquid, especially any extra liquid, out of the liquid line and into that tank. So it gives a liquid a place to sit when it's running in heat. And then when it runs in cooling, that gas line is now a discharge line. It heats up, creates pressure, and forces that liquid that's stored in that tank to go back into the liquid line.
Very interesting. In retrospect, at the time, I was just kind of like, probably like most techs are nowadays with a lot of things. It's like, well, I don't know. It holds charge somehow. Just magic.
Yeah, kind of an interesting thing. I've only seen that style of charge compensator on reams and roods. Trains and American Standards also have charge compensators, but the ones I've seen are really just kind of a large filter dryer shell with no dryer core in it.
If you work on ductless systems, then you know they can be challenging to maintain. And if you don't work on ductless systems, then you're just going to have to take my word for it. The fin spacing on the evaporator coils are very tight, and even actually the condenser coil fin spacing is also tight. And then they also have these blower wheels that are really long, and the cups on them are just tiny, and they tend to gather up gunk over time, and they just stop working efficiently if they get dirty at all. They get any significant grime on them, they stop working properly. So the challenge is with ductless is how do you clean them? Because often ductless systems are, they're mounted up on walls in places that you can't get water all over the place. So how do you clean them properly? And one way you can do it is you can pull them all apart. You can pull the blower wheels out, but even then, if you do that, you still have to worry about how you clean the evaporator coil. So what do you do? Pull the whole air handler off the wall? Well, never fear. RectorSeal makes the dissolve kit, and it's the word dissolve without the E on the end, as is very popular nowadays, to omit the vowel. So it's a dissolve, and it's a kit. It's also a cleaner, and so they have a cleaning solution that you can spray on the evaporator coil and blower wheel. But then it also has this bib that mounts underneath the air handler or fan coil, whatever you want to call it, and you can actually use a wand to clean that off, and it all funnels down into a bucket. And what's nice about the kit is that because everything fits inside the bucket, so you just keep the bucket on your truck. You've got the bib, you've got the little drain that drains down into the bucket, you've got the cleaner, you've got everything all there in one place. So it's a pretty cool kit. Check it out. It is the RectorSeal Dissolve Kit. Also, if you work on ductless, one thing that a lot of people struggle with is this idea of testing performance on a ductless system, because checking the charge is really tough on ductless. I mean, you can tell if the thing's flat, but other than that, it's tricky because there's so many moving parts. But what you can do pretty easily on most ductless systems is you can get a chart that shows you the different CFM output for the different stages of operation. Let's talk about the two different sides of the equation, because I think we are affected on both sides when it comes to high compression ratio in many systems because of the configuration, because now your condenser coil's inside and then your evaporator coil's outside. And so talk about that a little bit, some of the challenges that are generally faced.
One thing that's interesting about this, if you think about the relative size of the coils, in a standard air conditioning system, you've got more coil surface area on your condenser than you do your evaporator. Now, when we reverse that, that means that our coil surfaces are kind of opposite what we're used to when we're in air conditioning. And when it's cold outside, that serves us well because that extra surface area that's now on our evaporator helps us pick up the heat that we need. And then the smaller surface area on the condenser helps kind of pump your pressures up and keep your temperatures warm. That's sort of all on purpose, and it works reasonably well at fairly low temperatures, trying to help us keep the compression ratio down somewhat. But as it gets colder, there's only so much you can do when it's like you've got 5-degree air or 0-degree air going across your coil. There's only so much heat to gain, no matter how big your coil is. So the difference between your suction pressure and your discharge pressure increases, and that's when your compression ratio goes up and the amount of refrigerant you're circulating goes down.
And like you mentioned, it's the suction side that is more easily impacts the compression ratio. But then add in the fact that indoor airflow problems are so persistent in our industry. And now when you have indoor airflow problems, dirty filters, those sorts of things, that also can serve to drive up the head pressure in some cases significantly, because you're already sort of fighting the battle of having less surface area inside and smaller coils than you would normally. And that can cause you to kind of be working against it in both directions.
What can happen there, like with a airflow issue, is that not only do you get the high compression ratio, which of course hurts your capacity, but it hurts your compressor, because now you're not moving as much gas as it was originally designed to move, and so the compressor starts heating up. And that also confuses people some, how the compressors actually get hotter and work harder at cold temperatures than at hot temperatures. So as a general rule, the compressor will be operating cooler and be happier when it's 95 outside and you're in air conditioning than when it's 5 outside and you're in heating.
You make a really good observation there, and that ties directly into another place that we see issues with compression ratios, and that's in refrigeration. Because on a refrigeration compressor, let's say you're working on a rack or something, that compressor is much more concerned about the compressor. No, it's a compressor, it's an inanimate object. It's not concerned about anything, but it's much more damaged by high compression ratios than it is by the actual temperature of the refrigerant coming back. The idea would be, well, if you have a really, really cold evaporator coil and you've got a 10-degree superheat or whatever the case may be, then you've got cold refrigerant coming back. That should cool that compressor. But in actuality, it would be happier if you had higher load and the gas was actually denser coming back. That would actually do a better job of cooling that compressor, which is counterintuitive to a lot of us.
Well, the other thing is that when you get a hermetic compressor or a semi-hermetic compressor, really you're buying two things. You're buying a compressor and you're buying a motor that's matched to that compressor. And the match of the motor and the compressor depends very much on what you're going to ask it to do. So a compressor that's designed for a freezer, for example, really needs a different match than a compressor that's designed for an air conditioner. And that's another challenge with heat pumps, because you really are kind of asking it to do both things. That was one of the challenges in designing reliable heat pumps, is getting a compressor that could operate happily across those wide evaporator temperature ranges.
Well, and that's one of the real benefits to these kind of new generations of inverter-driven compressors, is that now as your compression ratio naturally starts to increase and that compressor is naturally no longer capable of maintaining the capacity, the modern inverter-driven compressor, whether it's a scroll or a rotary compressor, can actually increase its RPMs in order to continue to produce a decent amount of capacity, even at very, very low temperatures in comparison to its single-speed counterparts, which is a whole other conversation about the longevity or some of the efficacy of some of that from a serviceability standpoint. But from just a raw ability to produce the design BTUs, there's some clear advantages there.
Oh, sure. Yeah, it's really nice.
So let's talk quickly about how in refrigeration you can kind of have the opposite problem. In a heat pump, you have this highly variable evaporator temperature, but in refrigeration, you can have very highly variable condensing and some of the strategies that are used there, but that can also have an effect on compression ratio, correct?
Oh, sure. So one of the obvious differences with a commercial refrigeration system and a residential air conditioning system is that you have to operate year-round. So you can have a condenser operating in fairly cold weather, and you've got really a couple of things you have to do. One is most of your metering devices, or most of your common standard metering devices, require a minimum pressure difference in order to operate. So a lot of systems have head pressure controls, and the purpose of the head pressure control is to have a minimum head pressure no matter how cold it is outside, so that your expansion valve can keep operating. When you start forcing your head pressure up on purpose so that your metering device works right, well, there's an energy hit there in that you're increasing your compression ratio when you wouldn't have to. So a floating head pressure system, basically what you have to do to have that type of system is first you have to have a better metering device. So if you have a metering device that doesn't require a minimum pressure difference or requires a much lower minimum pressure difference, then you can let the head pressure go a lot lower, meaning that I can have a lower head pressure, a lower compression ratio, and use less energy to do the same amount of cooling.
Well, and then also in having that lower compression ratio, not only do you use less energy, but you also have much happier compressors. Clearly, because like we mentioned before, your compressor is happiest when it has a lower compression ratio. In my experience with compression ratios, they can vary wildly on like heat pumps. Like we just mentioned, if you have a heat pump where the evaporator temperature is dropping, because obviously from a very practical standpoint, your evaporator temperature has to at minimum be below your outdoor temperature. Otherwise, you're not moving any heat. And so as that evaporator temperature drops, your compression ratios are going to skyrocket. But on the air conditioning side, a modern high efficiency system may have a compressor that's designed for, say, a 2.7 compression ratio, 2.6 in that range. And then you go into heat mode where your compression ratio could be 5, 6, 7, 8, 9 in some cases. And obviously that's going to reduce the output of that compressor unless that compressor has some way of increasing its RPM or increasing its output. And that just shows you why it is so hard, or why manufacturers a lot of times shy away from wanting you to add refrigerant or wanting you to make charge adjustments in the heating season, because it's very challenging as those conditions change, as the outdoor temperature changes. But then also another thing we haven't talked about is that you may have a system that doesn't have visible frost, like a sheet of ice on it, but it may have some frost, and any amount of frost is going to inhibit the ability for that coil to transfer heat, which is then also going to have an effect.
True. To some extent, you have this problem also in air conditioning, but it's not as dramatic. If you look at, for example, superheat charging charts with fixed restrictions, what they're really telling you, when you see superheats in the high 20s and low 30s, what they're really telling you is the system is not at full capacity at that condition because of the lower head pressure. So that means, in effect, you have the same situation where you're not moving as much refrigerant because of the changed compression ratios. But there, they do actually go ahead and give you a guide for charging. It's just not as dramatic a change as you have in the heating cycle.
So speaking of awesome tools that I really believe in, I've always been a fan of the Bacharach leak detectors. And so I've been a user of the H10 way back all the way to before it was Bacharach, when it was Yokogawa and GE, the H10 leak detector, which became the H10G, which is now the H10 Pro. But we're not talking about that leak detector. We are talking about the Mac Daddy, basically the most accurate, high-quality leak detector made on planet Earth, as far as a portable leak detector, one you can actually carry around, and that is the Bacharach PGM IR. And you may ask yourself, you may say, well, what is special about the PGM IR? And I'm here to tell you. It actually has a display on it, so an LCD display that shows you the parts per million of a particular refrigerant when you're measuring. That really is the most awesome thing about it, is you can actually, as you're getting closer to a leak source, you can actually track the parts per million of a particular refrigerant type. And you may say, well, what you mean is an HFC or a CFC. No, a specific refrigerant. So like you can put in R410A or R22 or anything that you want, R4 or O7C, whatever type of refrigerant you're working on, you can put in that specific refrigerant. And the PGM IR will tell you with incredible accuracy how many parts per million there are in that particular vicinity, which means that you can actually start to sense a leak when you walk into a building. In many cases, you can actually walk into, a convenience store, into a house, and you'll start to pick up refrigerant if there's a leak in an evaporator coil. And so you can actually trace that thing down to the source. And we tried it. We've used it in a couple different applications, and it was just incredible. It also has just incredible resolution. So when you talk about accuracy or resolution, it can read down to 1 part per million with almost every refrigerant that exists out there today. And so it's just an incredible level of accuracy. It gives you that readout on the display, and you can actually select the refrigerant yourself. I'll tell you, it's not an inexpensive leak detector because it's a super high quality leak detector. But if you work in large commercial, you work in grocery store applications, or you want to have just literally the best leak detector that's out there. I mean, it saved us. We had a job that we were going to have to do a line isolation test to prove that the leak was in a line set. But with the PGM IR, we could pinpoint exactly the concentrations of refrigerant down at a line chase. And we actually did a video of that. If you go to TrueTech Tools and look at their YouTube channel, you can check that out and see that video of us using and demonstrating the PGM IR. And you can get the PGM IR from TrueTech Tools. So you go to TrueTechTools.com. You can get an excellent discount by using our offer code GetSchooled at checkout. Also, to find out more, this is what I'm going to suggest to you to find out more. So you're going to want to pause this so you can get a pen to write with. Just pause it real quick. Go to mybacharach.com, which is BACHARACH, mybacharach.com/HVACR school. So that's mybacharach.com/HVACR school to find out more. All right, to wrap this up then, what advice would you give the technician out there who works on a lot of heat pumps and they're in a market where they are below 65 degrees in a lot of circumstances? And there is obviously pressure in the industry to follow manufacturer specs. And of course, I say the same thing, follow manufacturer specifications. But in a lot of cases, you're in the field where manufacturer specifications may not always be easily found, or you may be working on older equipment. And so for somebody who walks up to a system and they just do a simple repair, let's say they replace a capacitor, but they want to verify this heat pump's operation. They want to make sure that it's doing what it's supposed to do. What suggestion would you give?
Well, that is a tough one. I do always start with whatever the manufacturer says. And sometimes you're right, what the manufacturer says isn't reasonable for your situation. I can remember years ago when a manufacturer was saying you should always just weigh the charge in. I said, well, that's no good unless I'm going from scratch. And I certainly don't want to go out and pull it all out and pull the vacuum and weigh it in just to make sure I'm right. That's not reasonable. The second thing that they offered was temperature difference, just measuring what the heat pump is able to do. And of course, there's a big gotcha there, is that you can't do anything with your temperature difference unless you also measure your airflow and know what your airflow is. But if you have standard airflow, then you can actually, from your temperature difference, calculate how much heating you're accomplishing. And if you look at the manufacturer's extended capacity charts, you can kind of work that back and see if it's doing what it's supposed to do. So, for example, if you're looking at this chart, Goodman actually has some really good extended capacity charts, and the thing I like about them is you can download them easily. You don't have to have a password or anything. But if you look at their extended capacity charts, you can see from at the outdoor temperature you're operating at how many BTUs it should be able to produce, and then you just work that backwards with your air formula to figure out what kind of temperature drop that would give you, or temperature rise, and measure your temperature rise, preferably close to the coil, not at the return and supply grills, because there's a whole nother host of issues you can come in with that. Preferably close to the coil. And if you got a temperature rise close to what the manufacturer is saying you should have, then you're probably doing what you're going to do.
That calculation actually is a little easier in heat mode than it is in cooling mode, because you're not having to deal with latent heat. Obviously, it's all going to be sensible, so that's fairly easy. And actually, another thing that's getting easier than it used to be is you have a much better chance of hitting close to your specified airflow now in the modern era of the ECM and the X13, because they are a little more tolerant to high-ish static pressure. If you look at most of the fan charts, until you get up to 0.8, 0.9, it's usually going to produce the designed airflow pretty close to it. So that makes it a little easier than some of the older ones. But again, you still have to have a situation where you've got a clean blower wheel. Obviously, it's just all the obvious things. You got to have the proper size blower wheel. It's got to be clean. You want to do a good visual inspection of the unit. But I do like that. I like that method. And I'm starting to use that more and more even on ductless systems. You know, that's another segment of the industry that it's very difficult to verify system operation on the refrigerant side. I talk a lot about the Testo 605Is. They're just little digital thermohygrometers that are very accurate. You can use 2 of those and very quickly confirm how many BTUs a system is delivering, as long as you can with at least reasonable accuracy, figure out what the airflow is. And like I said, with X13s and ECMs, that is a little easier than it used to be, at least.
Yeah, that's true. With the ECM system, you can feel pretty comfortable with the airflow.
Yeah, which for those of you who are thinking, well, why would that make any difference? On the old PSC motors, the static pressure changes all the way through the entire spectrum. So all the way from your static pressure being lower than 0.5 all the way up to 0.9, there's going to be a huge change in airflow, which you can measure static pressure, and that is something that you should do. But then throw in things like, well, what if the coil is a little bit dirty, or what if somebody put in a different aftermarket PSC and you didn't notice it? It just makes things a lot more challenging, where it's very easy to identify whether or not the system has a factory X13 or ECM, and just makes that job a little easier. I've been experimenting with that quite a bit lately, and it is pretty accurate using two 605Is and then just relying on the fan charts. And most of those are pretty easy to pull up nowadays. Most manufacturers, you can get those online in a couple minutes. Anyway, is there anything else that I'm missing on this topic, Carter?
Not that comes to mind immediately. I mean, this is something you could talk about for days, especially when you start talking about how to check heat pumps in the heating season. You can't really get very much agreement between manufacturers, much less between technicians. So it is a challenging job if you're a technician out there and working on a bunch of different equipment, and you're getting really kind of a different story from different manufacturers. If you just understand why they have the opinion that they do, it makes it a little easier to take. For example, I didn't really like the idea that they're saying we can't give you a charging chart for heating. And once I understood why they had a problem with that, it was a little easier to understand sort of their attitude on it.
Right. A lot of variables. The more variable conditions are, the more difficult it is to give a set answer,
right?
Because there's so many different moving parts. And when you're in service circumstances, you're not just dealing with, is it overcharged or is it undercharged? Is it slightly overcharged with a dirty blower wheel and a little frost on the outdoor coil? There's a lot of different things that could be going on all at once that could give you even the idea that it's okay when maybe there is a problem. But like you mentioned, verifying actual delivered capacity is always a good go-to when all else fails, and I think that's good advice. I am glad to find out that the Fundamentals of HVACR, the book that you co-authored, does talk about charge compensators. I must have missed that part there in my reading. So,
yeah, it's in there with a picture showing both cooling and heating cycle, how it works.
Very neat. So for no other reason than that, go look for that. You can find it on Amazon or a lot of online booksellers. You'll find it. Fundamentals of HVACR, co-authored by Carter Stanfield. So thank you again for your time, Carter. I think it's very valuable, and I appreciate all that you do for the trade.
Oh, thank you.
All right, so we've come to the end. We've come to the end of this episode of HVAC School, but I was just clicking around my computer. I'm going to click back to this right here and look at it. Yeah, Fundamentals of HVACR by Carter Stanfield and David Scaves is available on several different sites, but you can find it on Amazon. If you go to Amazon, you can find it there, as well as some other HVAC-specific bookstores out on the web. But if you just look it up by name, just search it by name, and you'll find it right there. And I would suggest looking for it. It's Fundamentals of HVACR by Carter Stanfield and David Scaves. And like he mentioned, he does talk in there about charge compensators. So silly on me for not noticing that, but it's something that I've seen in the field and never really took the time to understand. So thank you, Carter, for pointing that out to me and really just doing a great job on this episode. I thought it was really helpful, very, very applicable stuff that he brought to the table. As always, you can find out more about all the podcasts in the Blue Collar Roots Network by going to bluecollarroots.com. That's bluecollarroots.com. We have the Tool Pros podcast, Service Business Mastery, HVAC Building Science, HVAC Shop Talk, The Tradesman, and several others that you can find by going to bluecollarroots.com. But once you find them there, don't stop there. No. Go to your podcast player of choice on your phone, which is the other thing that I suggest that you do for HVAC School if you care about hearing it regularly, and subscribe to it there. Every different way of listening to a podcast, every application out there, you should be able to find all of your favorite HVAC and trade-specific podcasts in the Blue Collar Roots Network, whether that is the Google Play Store or whether it's the Stitcher app or whether it is the podcast app directly on your iPhone. You should be able to find them all those places. In fact, you should even be able to walk up to an Amazon Alexa and say, Alexa, play the HVAC School podcast. But if my experience is any guide, it won't actually work because I haven't been able to make that work yet. But theoretically, that should also happen. If you have not signed up for the Daily Tech Tip, I would ask you to go to hvacrschool.com, sign up for that. I've been doing them a little less than daily the last little bit. I've had a lot of things going on, but I've been doing them about 3 times a week with new content and then recycling some old stuff. Actually, today I'm going to be publishing one on keeping warm through the cold winter because this is the first cold snap in Florida, and I'm literally freezing my buns off because in Florida we are just not used to anything below 40 degrees. It's a total carnage. I had a little frost in my windshield. I absolutely did not know what to do with it. It was freaky. So anyway, in Florida, we get a little bit of cold weather. We got to stay inside, and we realized, my wife and I were talking about some movies we could watch, and I realized I never watched the movie E.T. before. At least not as an adult. I saw it as a kid, but we never watched it again as an adult. And I thought, let's watch it, kind of for nostalgic reasons, and put it on. The kids are watching it, and one of my daughters looks and says, "Dad, what's E.T. short for?" I'm like, well, that's obvious. It's because he has little legs. All right, we'll see you next time on HVAC School.